Hi guys, welcome to my channel again. My name is Malasa. Today I'm gonna be show you how to define the cross section and material of a 20-story building. In the previous tutorial, I have already shown you how to define the grid and grid systems of this 20-story building. And now today I will proceed the tutorial number 2, which is a definition of section and materials that are going to be used during the next modeling and designing of this high-rise building. So to continue, let's open the grid systems that we have defined before. So good, now it is open. So just to define the material, go to the define menu and then the material and property. So I have two basic materials that are going to be used during the modeling and design of this high-rise building. Those are the first one is reinforcement bar and the second one is reinforced concrete. So to do this, we need to add a new material because all those are a default material which I've already set in ACI code. So now add the new material here. The region is United States. So as I'm going to use Eurocode and the Ethiopian building code of standard, so I need to select the Eurocode. If I wanted to use an Indian code, I can select India. And if I wanted to use the Chinese code, I have to click this China. And if I wanted to use the ACI code, I have to click this United States. So now, for the time being, just collect Euro. And the material type is here. I am going to use the concrete and steel. First, I have to define the concrete cross section. And now here the standard that I'm going to use is the European standard or Ethiopian building code of standard. Since the two codes are similar, then I have to select this one. I have two types of concrete grade. Here I have to select the C2530. Click OK. So here C2530 concrete grade is open. So all those properties are associated with these grades of the concrete. So the etabs will automatically takes all the mechanical properties of C2530 grades of concretes. And here no need of just modify all those parameters except the Poisson's ratio. Here the material type is concrete. The directional symmetry type is isotropic because uniformly I'm going to use concrete for the whole length of the member. So the material display color is this one. Now if I wanted to change, I can change it. So the material notes here, if I wanted to write something here, I can write there. And the material weights and the mass is here. So the specified weight density is 25 kilonewton per meter cube. And when I come to just specify mass density, it is the unit per unit volume is kilonewton, and that is kilogram per meter cube. So the modulus of elasticity E for this specified grade of concrete is this one, that means 31 gigapascal, and the Poisson's ratio is 0.2. Now etabs by default takes the Poisson's ratio U 0.2, but here we have two parameter, two property of concrete. The first one is the cracked concrete and the second one is uncracked concrete. for the time being, as the concrete has a cracked behavior, I need to consider the cracked behavior of the concrete. So for cracked behavior of concrete, I have to use 0.00. So this is specified in Ethiopian Building Code of Standard and in Eurocode standard. So when I come to the coefficient of thermal expansion, just I can take this one. So here, as you see here, this one, this automatically, this is a function of the Poisson's ratio and the modulus of elasticity. Okay, now here, now let me show you the relationship between the shear modulus and the modulus of elasticity. Here, there is, it is, I think, opening. So here, the shear modulus, that is G, which is equal to the function of the modulus of elasticity times the parameter, which is 2 into the 1 plus, I think this is equal to E over 2 into 1 plus the Poisson's ratio of V. As the Poisson's ratio of V is taken 0 plus 1, that is 1, 1 times it is 2, so the modulus of elasticity E over 2 is the shear modulus. That means 31,000 divided by 2, which is 15.5 gigapascal. So etabs will automatically calculate the shear modulus from the provided Poisson's ratio and modulus of elasticity value. Now here, after that, just go to the modify or show material property design data button here. So when we come to here, there is the grade of concrete, which we have already defined before. Here, this is C2530. The material type is concrete isotropic. Now the here, when we see this, the characteristic concrete cylinder strength FCK is taken and written here. That is because the compressive strengths that are going to be used for the design of the concrete, the characteristics concrete cylinder strength, that is FCK. Here, for example, in this value, this 25 is the cylindrical compressive strength at 28 days, and the next value, which is 30, is the cubical compressive strength, which is taken at the day of 28. So etabs will automatically takes this cylindrical characteristic compressive strength from the provided grades of the concrete. So if we wanted to use a lightweight concrete, so we need to click this one. But for the time being, I will not be using lightweight concrete. So now click OK. Here, now click OK. Now here, the material damping property data must be filled here. The damping ratio of concrete that are going to be used for modal analysis will be taken 5%, that is 0.05. So now click OK. So here, click OK. If I wanted to modify these grades of concrete, just click modify show material, and I can write the place where this grades of concrete is going to be used, that is at slab, beams, and mat slabs. So click OK. So now here, so add copy of this material. No copy of this material, because I have to add new grades of concrete for vertical member, that is C3545, this one. Now click OK. This is for shear wall. For vertical member, so here all those parameters should be taken as it is except the Poisson's ratio. Here this Poisson's ratio must be taken 0 for the cracked concrete. This value is specified in Eurocode and in Ethiopian building code of standard. So now here, just when we come to this one, this is for uncracked concrete, V should be for uncracked concrete, V is equal to 0.2, and for cracked concrete, V is equal to 0 for cracked concrete. So this is specified in European Code of Standard, this or Ethiopian Building Code of Standard. So, and similarly, the damping ratio is 0.05. Then all the other parameters are similar. So now, okay. You now click OK. So now define also the other material, which is steel. That is, this one must be reinforcement bar. So here there is no any standard reinforcement bar grade associated with the Eurocode and Ethabs 2016. So now click OK. We will edit it. We will just define it manually. So I can use 500 megapascal steel grade here. So here we have the boundary limit for the yield strength starting from 400 to it is 600. This is the boundary of the yield strings of reinforcement bar that are going to be taken during the design of reinforced concrete structures. So here we can take the 500 grades of reinforcement steel. So this is the reinforcement that is which is a rebar, and all the smart materials must be taken as it is. So here go to the property design data. Now here the minimum yield strength is, that is FO, the minimum tensile strength is FU, the expected yield strength is FYE, and the expected tensile strength is FUE. So all this value must be filled based on the Eurocode and the Ethiopian Building Code of Standard. So to do this, here we have the relationship between the yield strengths and the tensile strength of reinforcement bar based on the ductility. Here, this F is the tensile strength of reinforcement bar, and Fy is the yield strength of the reinforcement bar based on the classes of ductility. Here now, the ratio of the tensile strength to that of the yield strength is called the elongation, which is designated by AGT in Ethiopian Building Code of Standard, AUK in Eurocode Standard. So now here, this RM is the tensile strength, and the yield strength is designated by this RE. So the ratio of RM over which is the yield strength is RE, which is equal to AGT, where AGT is the elongation of the reinforcement. I mean at the maximum force in this one. So now let's come to the graph which shows the strength of reinforcement bar. So now come to here, this graph, this one. So now here the greater the value of Ft over Fy, that means Rm over Rd, and EU or AGT, the greater the ductility class. Here we have three ductility classes of reinforcement bar. That is ductility class A, which is this one. Which is this one, and ductility class B, which is this graph, and ductility class C, which is denoted by this graph. Here, this one. So here, this value, and this value is called the tensile strength of the reinforcement bar at a value of AGT. This AGT. So all these are the grades of the reinforcement bar. This is basically for 500 grade, but it is similar for 600 and 400 grade. So the ratio of the tensile strength to that of the yield strength should be greater than 1.05 for in the case of the class A reinforcement, and in the case of class B it has to be greater or equal to 1.08. In the case of class C, it has to be greater or equal to 1.15 up to 1.35. This is the boundary. So based on this formula, that means that is Ft over, that is Fy, which is equal to Agt. So suppose if we have the elongation, that is 10%, that means 1.1 times Fy, which is equal to the tensile strength of reinforcement bar. So here, using the provided elongation, so we can calculate the tensile strength of the reinforcement bar for a specified grades of reinforcement. So having this in mind, yes, we come back to this one. If I can use 500, so I can use here, it is 500, and this one is for 10% elongation, that is 550, and this one is, I can take 500, and this one is 550. So now click OK. Here the damping properties of the material, it has to be 0.05. So now click OK. So here click OK. This is the definition of the reinforcement bar that is going to be used for the design of this high-rise reinforced concrete structure. So now click OK. So we have already defined the concrete and the reinforcement bar. Then we need to also define the cross section here. So to define the cross section, we need to delete the unnecessary cross section here. So I need to delete this one, composite structure cross section here. Okay, now let me define the cross section of the column here. So to do this, we can select the default column cross section and go to the modify menu. And here C 900 by 900 is one of the cross section of the concrete. So select the vertical member here. Then here the color can be set just like this here, this one, because it is easily visible. And now here it is the concrete rectangular cross section. So this one is make it 900, and here make it this one also 900. So just to go to the stiffener modification dialog box. So here as the concrete is it is a it has a cracking behavior. So the cracking behavior of the concrete must be accounted in modeling and designing of this high-rise building. So we need to account the cracking behavior of the concrete by using a stiffness modifier. So we should not take 100% of the stiffness for the design of the structure, because some percentage of the cross section will not be ineffective. So we have to deduct, or we have to reduce the ineffective cross-sectional area of the concrete cross-section by using a stiffener, the stiffness modifier. So the Eurocode and the Ethiopian Building Code of Standard recommend us just to use only 50% of the moment of inertia and 10% of the torsional constant value, and also the 50% of the shear area. So we need to use this 0.5 for shear, and for torsional 10%, that is 0.1, and for moment of inertia it is 0.5. And here now click OK. So the rest, the modify show reinforcement bar cover with respect to the column here, and this is we have to assign the reinforcement grade for column, and here we need to also provide the clear cover for the confinement bar, that is 25. And when we come to the number of longitudinal bar along 3 direction, that is we can take it 5. Later it will be changed. This is the preliminary number. And the longitudinal bar size going to use is 20 in both 2 and 3 direction. And the corner bar is 2, and the middle bar is 20, and the corner bar is 20. When I come to the confinement bar, I have to use diameter 10. So now click OK. So here now click OK. So this is one of the cross section of column that is going to be used in this high-rise building. So just based on this provided definition of cross section, I can define all the rest columns just by copying the properties of this column. So to do this, select this one and add copy of the property. So here I can take 9, that is C 900 by 800. So I have to change this to 800. All the rest are similar. Now click OK. Now add copy of the material, the property also. So here see 800 by 800. So I need to make it 800 and click this one. So add copy of the property. Then here I have to make it 800 by, this is 600. So I need to make it, that is 600. So click OK. So add copy of the property again. And this one is 60 by 60. Sorry, 60 by 60. So I have to make it 600. Then click OK. Now add copy of the property of this column also to the other column, because it saves time. So now see, that is 600 by 500. So I have to make it 500. So click OK. So add copy of the property again. Then here make it 500 by 500. Then make it 500. Then click OK. So add copy of the property to also the other column. Then 6, that is 500 by 400. And I have, that is 500. I have to make it 400 and click OK. Then add copy of the property again. Then I have to make 6, that is 400, that is 400 by 400. Then make it 400. Then click OK. Then add copy of the property also to the other section. Then that is 400 by 300. So make it 300. Then add copy of the property also to the other column. Then make it 300 by 300. This one. So all these are the cross section of the columns that are going to be used during the next modeling and design works of this high-rise building. So here the minimum cross section is, it is 300 by 300, and the maximum cross section is 900 by 900. So the design section will be between all those cross sections. If there is another optimized cross sections which will be required during the design process, then I can define it later. So now click OK. And now next I will define the cross section of the beams. Just go to do this, go to the frame property and add new property. Then select the this one. Okay. So no need of just add new property because I have already this default cross section, so I can edit that one. So That is the first beam is the basement beam, which has a cross section of 600. That is 350 by 600. So select the material which is for beam, and this is 600, and this one is 350. And go to the property modifier and provide the stiffness modifier here. It is 0.5. So just copy and paste, and here, and this one is 0.1, and this is 0.5. Only the 50% of the cross section must be taken into account to account the cracking behavior of the concrete beams. And now here modify the reinforcement cover here. So this is the cover to longitudinal rebar centroid, which is I think here, if I use, this is the diameter 20 main bar for beam, and here I have a strap here, then I have a cover of 25 here. This is 25 plus, if this is diameter 10, then the distance from this up to this is 25. That is 25 plus, this is 10 plus to the centroid of the main bar to this, that is 10. So totally, which is 45. So I have to make it 45. Then I can copy this to the bottom bar, and here assign the grades of the reinforcement bar for beam. And this is reinforcement area override for ductile beam. It is no need. Then here the I think all are defined. Then click OK. So add a copy of this property to the other beams. Then this is edge beam. That is 200 by 600 cross section. That is 600 by 200. So click OK because all the other properties are defined before. So add a copy of the property for the other beam also. Then here, this is the the tip beam. That is 250 by 800. It is 250. So the width is 800, and the depth is 250, which is similar to the flat slab. So click OK. So add copy of the property again. So here, this one is the mechanical beam, because the mechanical floor is not a flat slab, it is a two-way slab having beams in both x and y direction, and the depth of the size of the beam is 300 by 500. So this is 300, and this one is 500. So now click OK, and one more beam remains. Add copy of the property. So here it is beam 250 by 600, and make it is 250, and make it is 600 now. Okay, I think this is all about the definition of beams and columns. So next I have to define the cross section of the slabs. So to do this, I can take these default cross sections and modify it. So this is the ramp beam, I mean the ramp slab. So I have to assign the concrete grade here. So I need to use the shield 10 because it is a thin member. If I'm going to use a matte slab having a thickness of 1 meter, 80 centimeter, or just like that, I have to select shell thick. But this, for the time being, shell thin represents the thickness of this slab. And here, this is slab, and I have to select. I have to make the thickness of the slab, which is around 200. And here I have to modify the. Sorry, I have to modify the. Where is this? Okay, sorry, 200. Modeling type is 13. Ramp slab. The thickness is this one. Okay, now modify. So here I have to define the stiffness modifier here. So to do this, click this one. So here, just before writing the stiffness modifier value, now let me just describe what does membrane F11 direction mean, and what does shear V23 direction mean, and what does all this direction mean. So just now let me describe the concepts about this, the places where the stiffness modifier will be applied. Here, okay, this one is this is a shell element. It may be slab, or it may be wall, or just it may be beam, or it may be a column. So here it has 3 faces. So this face is phase 1, and this is phase 2, and this one is phase 3, which are designated by the direction of the local axis. So F22 means the axial force which is applied along the local axis 2 on the faces of 2. And when we come to F21, this is the axial force which is applied at face 2, but along the direction of the local axis 1. It just in this direction. And when you come to V23, this is the shear force which is acting on phase 2 along the direction of the local axis 3, this one. And the similar interpretation can be provided for all the rest phases. So having this just concepts into mind, just we come back to here. This is the the in-plane deformation, and all these are the out of plane deformations. So here, all these are, this is out of plane deformation, and all these are the in-plane deformation. So the stiffness modifier will be provided for the in-plane deformation and the out of plane deformation. Basically, the shell elements can undergo both the in-plane deformation and out-of-plane deformation. So we can provide it, that is 0.5, that is 50% of the stiffness can contribute for the design of the section. That is why, because the shear is which has insignificant effect on the shell element, it has significant effect on a beam element. So just click OK and click OK. Now add copy of this property to the rest slabs, that is basement slab. So the thickness is 180 because it is a two-way slab having a beam structure in both x and y direction. So now click OK. So add a copy of this property. Then we have to provide a thickness for a flat slab. Flat slab 250. Then here I have to make it is 250. So now click OK. So add a copy of this property to the rest slab. That means the west slab, that is 180, 100, so 180. So I have to make this 180. So okay, add this property to the other slabs. So this is the landing, that is 180. So make it 180. Okay, add copy of the property also to the other slab, that is roof slab, which is 170. So here make it 170, then apply and add a copy of this property also to the mechanical slab, which is 160. Then make it 160, then click OK. So I think all those are the thickness of the slabs that are going to be considered in the modeling and designing of our slab structure. So finally click OK. So, and what is left? The definition of the wall. Now to define the wall, we need to go to the wall section here. So I can take the default wall property so that I can edit now. That is wall 500. So here we have to assign this concrete grade for this shear wall, and now here I have to make it 500. So I have to define the stiffness modifier again, 0.5 here. So now this will be applied to the in-plane and the out-of-plane deformation. And this one now shear has an insignificant effect. Then okay, now add this property to the other wall, that is wall 400. So make it 400. Now okay, so add a copy of this property to the other shear wall, that is 300. So make it 300. Now click OK. So, and add a copy of this property to the retaining wall. That is 250. Then make it 250. Then click OK. I think this is all about the definition of the material, such as the reinforcement bar, and the concrete, as well as the sections such as the columns, beams, the slabs, and walls. So this is all about for today's tutorial, which is tutorial part 2. Next time I will be showing you how to model this 20-story building using the provided cross sections of member. So thank you for watching. Bye bye.